Today we are moving on to section 11.2. In our last lesson we talked about parametric equations and what those are algebraically. That is an x equals and a y equals equation where both functions are defined by a third variable, t. And we looked at how to work with those moving back and forth between the parametrics and the xy or the Cartesian equations. In this section, we're going to look at how to do calculus on parametric equations. So the same calculus ideas that we've learned this year, we're now going to apply to this new kind of function. So to take a derivative, what we're going to do, a derivative notationally we've defined as being dy over dx. So to find that, we're going to find dy dt, the derivative of the y equation in terms of t, and divide that by dx dt, the derivative of the x equation in terms of t. And then algebraically, if we think about like multiplying by a reciprocal, those dt's would cancel each other out and we'd be left with dy over dx, which is what we're going for when we talk about a derivative or a slope. So we're going to be able to find now a derivative or a slope of a parametric equation defined as dy dx. And then from that slope, we could find tangent lines. To find an equation of a tangent line, remember we need a point and a slope. So we would need an x comma y point, and then we can use our dy dx as a slope. And we'll look at an example of that. If we want to take a second derivative of a parametric, what we're going to do is take the derivative of the first derivative. So we're going to find that dy dx the way that we talked about here. Then we're going to take the derivative of that dy dx, but we're going to take the derivative of it in terms of t because that's going to be the variable in there. So we're going to take the derivative of dy dx, but in terms of t. So that's what that top means, the dy prime, the derivative of dy, but in terms of t. And then since we're going to have this weird variable thing of like dt's, but really we want it dx, we're going to need to divide by the dx dt, again, the original derivative of the x. So we're going to take our first derivative, find dy dx, take the derivative of that, but furthermore need to divide by a dx dt to get all those dt's to cancel out the way that we want, and so that we have the second derivative of y and the second derivative of x, the dx2 there. And we'll look at an example of how to do that. So this is actually a picture of a problem that we're going to do in just a minute, where the blue line there is the parametric equation defined by x is equal to the secant of t and y is equal to the tangent of t. And then that red line there is the tangent line. At the point where t is pi fourths, and we're going to look at how to find the equation of that tangent line. This is an example we're also going to do where what we're going to want to do is find the length of this parametrically defined curve. So this curve is defined as x is equal to cosine cubed of t and y is equal to sine cubed of t, and we're going to want to find the length of this. This is called an asteroid. It's not an asteroid, like that would need an extra E in it, and it's not like a typo. Yes, it's still like star-shaped, probably connected in some way, but anyway, not asteroid like you may have, heard of celestially, but just asteroid. But it is a star-shaped function. And the important thing to note from this picture before we go into the example is the symmetry of the curve. Notice that it's really four sections that are all the same. And so when we think about defining curves in terms of pi's, remember our unit circle, and so we've got, see if I can point the right way on the video, that way, and we've got 0 over at the positive 1, and then up would be pi halves, and so what we're actually going to do is just integrate from 0 to pi halves, just finding that first quadrant length, and then multiplying it by 4. The reason is, if we actually tried to just integrate between 0 and 2 pi, we'd actually get an answer of 0. And clearly this thing does have a length, so we would run into a problem there because remember that 0 and 2 pi in many cases in a trig situation, when we're thinking about graphs, actually mean the same thing. So it would give us a false solution there. So we're going to use the symmetry of this, that each of those 4 quadrants have equal length. So we'll find the length in one quadrant and then multiply it by 4. So the idea of length we've talked about earlier this year, that if I wanted to find the length of that blue curve, I could approximate it by connecting some points along it and measuring those straight line distances. It wouldn't be perfect, it'd be short, but if I used more and more and more of them, it'd make it better and better and better. And then we'd add those all up, and our fancy adding machine in calculus is the integral. So each of those little lengths could be found by a Pythagorean theorem. A change in x and a change in y. Pythagorean theorem would give us that diagonal length change, and then we add those all up. So that's what we find here for our length equation. So in our length, we're going to take the integral of, and then that's a Pythagorean theorem in there, where the f prime of t is like the x equation, and the g prime of t, that's the y equation. So the derivative of the x, square it, the derivative of the y, and square it. And that will give us each individual length, and then the integral will add those all up for us. All right, and that is the end of the slides that I want to show you. So now we'll go to some examples. All right, so the first example is that one where we're going to find a tangent line. So in finding this tangent line, we're going to define our equations as x is going to be the secant of t, y is the tangent of t, and we're going to be working at the point where t is equal to pi fourths. And we're not going to use decimal approximations here. We want to use exact trig values. Pi fourths is a special angle, so we're going to use our exact trig values for that. So I'm going to draw out our triangle for pi fourths. When we think about pi fourths, that is a 45-degree angle, pi being the conversion to 180 degrees, and then 180 divided by 4 is 45, and that's a 1 square root of 2 triangle there. So if we take the secant in that triangle, that would give us our x value, because x is the secant of t. So the secant of pi fourths, well, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So hypotenuse over adjacent, we're going to get square root of 2. And then tangent is opposite over adjacent, so that's going to be 1. So that's going to be our x comma y point. So to write a tangent line, we need 2 things. We need a point, which now we have, and we need a slope. And that's where the calculus comes in. That slope is derivative. So we're going to find dx dt, the derivative of the x equation in terms of t. So the derivative of secant, you might need to look these back up if you don't still have them in your memory bank. The derivative of secant is secant tangent, so we get secant t tangent t, and then dy dt, the derivative of tangent is secant squared. So we learned these a long time ago, back in Calc 1. Kind of had them memorized for a while there, at least for the most part, but it's been a while since we've used them, so they might be a little bit foggy, so you might need to look those back up again, these trig derivatives if you need them. Okay, but what we want to find is dy dx, slope. So to find dy dx, we're going to take dy dt and divide it by dx dt, because that will give us dy dx. So the y derivative was secant squared, and the x derivative was secant t tangent t. And then we want to evaluate that at our point. Before I do that, I'm going to do a little bit of simplification here, and that I can cancel out one of those secants. And so we're going to say that this is just secant of t over tangent of t. We can maybe simplify those further by turning them into sines and cosines and looking to see if anything reduces, but I'm not going to bother with it because I can evaluate those at pi fourths. So the secant of pi fourths we've actually already evaluated. That was square root of 2, and the tangent at pi fourths was 1. So that's our slope, our m value. So then I'm going to use that point slope form where we do y minus y1 equals m times x minus x1. Or you could just use your y equals mx plus b and solve for your b value. But in this one, we're going to have y minus y is 1, m is square root of 2, x minus, and our x value in our point is also square root of 2. Clean this up a little bit by distributing the square root of 2 through there. That would make minus 2, and then when I add 1, it's going to make minus 1. So there's our tangent line, y equals mx plus b tangent line. So this line shares the point with the original parametric equations, and it has the same slope as the parametric equations. Okay. So writing the equation of a tangent line, we need a point and a slope. To find a slope, we're going to do the dy over the dx. In our next example, we're going to look at finding a second derivative. So we're going to find the second derivative of y in terms of x. And we're going to use x is t minus t squared, and y is t minus t cubed. We don't have a specific t value here to find this, so we're just going to find it notationally with t's in terms of t, and then we can plug in any t value we would want after that, but there's no specific t value. So to start this, we're going to find dy dx. So we're going to find dx dt, which is 1 minus 2t, just using our power rule, and dy dt, 1 minus 3t squared, again, just using our power rules. And when we put those together, dy dx is going to be the dy over the dx. Nothing simplifies here. We cannot cancel out those t's because of the addition and subtraction that's happening there. So can't cancel out the ones. No canceling can happen. So this is our first derivative. Now to take our second derivative, what we're going to do is take the derivative of that. Now to take the derivative of that, we need our quotient rule because this has a quotient, a division. So we got to remember back to, again, Calc 1 and the quotient rule. So quotient rule low, that's the bottom, d high, that's minus 6t, minus high, d low, the derivative of the bottom is negative 2. That is all over low, low. But then there's another thing that comes in when we take that second derivative. And this is where we take the derivative of the first derivative, but we just took that derivative in terms of t, and we don't really want it in terms of t. We want it in terms of x. So we need to divide by dx dt. So we're going to take that whole thing and we're going to divide it by 1 minus 2t. Oops, and I forgot my low. I forgot my squared on that quotient rule there. But then we're going to divide by that dx dt. So we're going to divide by 1 minus 2t. All right, so now we are going to try to clean this up because this is really just like a royal mess here. So in cleaning this guy up, let's see. There we go. All right, so on the top, I'm going to distribute. So I've got minus 6t plus 12t squared. Then I'm going to distribute this negative 2, but I'm also going to distribute that negative. So it's actually like distributing a positive 2. So I'm going to have plus 2 and minus 6t squared. On the bottom, I am not going to distribute out the squared. And then instead of dividing by that 1 minus 2t, I'm going to think of multiplying by a reciprocal, right? That's the same thing as dividing. So I'm going to put that onto the bottom of a fraction. So now I don't have a fraction inside of a fraction anymore. I'm going to multiply by the reciprocal there. So now, lastly, on the top, looking to combine like terms. See, my constant is 2, linear minus 6t, and plus 6t squared. You could put those in the other order if you wanted to. It doesn't really matter. over on the bottom now, those groups are actually exactly the same. So I'm going to have 3 of those groups, right? And that is our second derivative. That is the second derivative of y in terms of x. So to take a second derivative, excuse me, to take a second derivative, take the first derivative doing dy dx and then divide that by dx dt. Since we took a derivative then in terms of t, we need to cancel out that in terms of t and switch it out for an in terms of x. So we do that with the dx dt. All right, so next example, which is our last example, is the arc length question. So this is that one where it was the asteroid, the little kind of star-shaped diamond thing, and we're going to find the length. So that was defined as cosine cubed, x is cosine cubed of t, and y is sine cubed of t, and we're finding the length between 0 and 2 pi, but remember that what we're actually going to do is only find the length of one section, one quadrant, and then multiply it by 4 using the symmetry in the graph. So the length equation was that we're going to integrate a Pythagorean theorem, which is going to be the dx and the dy both squared and square root of that. That's going to be our length equation, which is the length equation we used before when we did x and y functions, except our dx or our dy was just equal to 1 because we were taking it in terms of that variable. So dx is 1. But now they're both dx dt or dy dt. So now they are both functions. They're not equal to 1. So find dx dt, chain rule, multiply the 3 down, lower the power, times the derivative of cosine, which is negative sine. So I put that negative out front, so I got the equals and a negative out there. Derivative of cosine is negative sine. Then dy dt, again, chain rule, 3 out front, lower the power, times the derivative of sine, which is cosine. Okay, so now my length. I'm going to do 4 times 0 to pi halves using that symmetry. And I'm going to do a square root of each of these things squared. So now when I square them, I have to square each part of the product. So square a negative 3, that's 9. Cosine squared, that's cosine to the 4th. And sine squared, oops, I forgot my t, and t. So cosine to the 4th t and sine squared t. That's that first one squared. And then square the second one. 3 squared is 9. Sine squared is now to the 4th. And cosine squared. And that is dt. Okay, so this is pretty messy. We can actually clean this up a little bit by factoring. So we're going to take out common factors here. So each of those have 9, and they each have at least a cosine squared and a sine squared, which leaves a cosine squared in the first piece, and it leaves a sine squared behind in the second piece. Now, I know you don't know probably a lot of your trig identities, haven't really had to memorize those at any point in your curriculum, but hopefully at least what's left in those parentheses rings a bell for you as being the Pythagorean identity. Sine squared plus cosine squared or cosine squared plus sine squared is equal to 1. So that whole thing's equal to 1, and since this is a product, that really means it just goes away. And so then everything left is actually, so this part here is really just 1. So that's just times 1. So it doesn't really matter. And then everything left underneath there is still a product. So we can take the square root piece by piece then. So that gives 3 cosine t sine t dt. Now to integrate this, I think we would need another substitution. I think like a double angle substitution or something, which again, I don't think you have memorized. I don't have memorized. I'd have to look it up on a chart and try to match it up with what one it looks like to me. So at this point, I would just throw this into Desmos. And then, yes, if we're going to throw it into Desmos, we probably could have just done that on step 1 instead of simplifying, but it's always good to review those algebra skills as well. So when you put this into Desmos, it's going to seem like it's maybe giving you a wrong answer, because doesn't it feel like this is probably going to be really messy, right? And just like looking at that curve, that star, it just seems like it's going to be really messy, right? It's 6. The answer is 6. Each quadrant has a length of exactly 1.5. And so then those 4 quadrants together add up to a full length of 6 for that asteroid. So in this section, we learned how to take those parametric equations that we talked about in the last section, how to take a first derivative, and from that make a tangent line, or from the first derivative take a second derivative, and then how to find the length of a parametrically defined curve. Length is actually a really important concept when it comes to parametrics, because again, a parametric is kind of plotting a point in motion. So how are the x and the y values of a point changing over time? So when we find the length of the curve, what we're doing is finding the length of the path that that particle is taking, and that could be a really important thing to know. So length is an important concept in parametrics. So that's why we focused in on this one. So whatever questions you have, send them my way. I'm happy to help. See you again soon.